We are introducing Ohm's law. And Ohm's law describes the relationship between voltage and current of a resistor. And so the simplest passive element in an electric circuit is a resistor, and it always consumes energy. Always consume energy. This is consume energy, and it's a passive element. The relationship of voltage and current of a resistor can be stated as the Ohm's law. So this is the Ohm's law, and voltage V equals current times resistance. Okay, and it's a linear relationship. So if you draw the relationship on this IV plot, if you put current I as the horizontal axis, voltage V as the vertical axis, so you will draw a line. You will draw a line, and the slope is R, is its resistance. Okay, so we say R is the resistance of a resistor. So this is resistance. And so the larger the voltage that it is applied to a resistor, uh, the larger the current, right? They are proportional to each other, and the larger the current flowing through a resistor, the larger the voltage across that resistor. Okay, so you can draw a symbol like this. So this is the symbol of a resistor, and the direction of the current is flowing into the resistor. And because it is a passive, it is a passive element, it always consumes energy. So if you remember previously we talked about this this block can be any electric device. So if the current direction is like this, and if we are given positive and negative terminals of those blocks, it means this device always consumes energy, because if it consumes energy, the current always flows into the positive terminal. So it's consume energy. Uh, or in the opposite, if it's something like some element like this, and current, this is direction of current, and this is positive, this is negative, then this is an active element, and it could be a power source. Okay, or it could be a current source or voltage source. Okay, so here, because a resistor always consumes energy. So as long as we know the direction of the current, we can immediately define the positive and negative terminal of a resistor. And so we have this, and then it's the voltage across the resistor is V. Okay, so this is Ohm's law. And there are several forms of Ohm's law. So it can be written as this, or it can be written as I equals V divided by R. V divided by R. Okay. And we go to the next page. Next page, there are two examples. And So we have in the example 2.11, we have a resistor, and we already know that the voltage across this resistor is 5 volts, and the current flowing through the resistor. So it's because it's a resistor, so the current flows into the positive terminal and flows out from the negative terminal. Okay, the current flowing through the resistor is 25 mega ampere. So by Ohm's law, so we have this V equals I times R. So V is 5 and I is 25 times 10 to the power of minus 3 times R. So R is, this is 525 times 10 to the power of minus 3, and which is 200K. 200, not 200K, which is 200. The unit is ohm. So the unit of a resistance is ohm. Okay. And we look at example 2.12. Find the current I in the circuit shown in this figure. So in this current I, no, in this circuit, we have a voltage source, and it connects only to a resistor. Oh, by the way, the line here, it means electric wire. It means electric wire, and we assume it's ideal, so it doesn't consume any voltage. Okay, so this is electric wire. Electric wire. And here, you need to find the current I. First, we need to find VR. So find VR first. How? By KVL. So KVL tells us the summation of the voltage inside a loop is 0. So we talked about KVL last time. I always start from the bottom left corner, and then I go clockwisely. So when I meet a negative sign, then it's -3, and then this is positive VR, and then go back to the same node equals 0. So we know VR is 3. Okay, and but when you become more and more familiar with the problem, with the circuit, you should immediately know that VR is 3. And the reason is it has a power, it has a voltage source. And after the loop, it needs to consume all the voltage to make it 0, because it needs to always satisfy KVL. So we can immediately just write down that this VR, and this is positive and negative, and VR is 3 volts. So if you but at least you need to calculate VR by using KVL. And then after we know VR and we want to find out I, and then we can apply Ohm's law. So I equals VR divided by 3.3K, which is 3 divided by 3.3K, which is 0.91 milliampere. Okay, so this is the answer. Okay, it's very basic, and Yeah, let's just go to the next slides. Okay, so the first part repeats, so please ignore. And in on these slides, I want to talk about resistivity, resistivity of a resistor. So uh, the conducting performance of a resistor depends on first material, what kind of material it is made of. Second, the geometric shape of this resistor. So the resistance R, we usually use a capital R to represent resistance. So R is resistance. Equals rho. Rho is resistivity of a material. The unit is ohm meter. So resistivity times L is the length of the resistor divided by area, the cross section area of a resistor. Okay, so L and A are length and area. And regarding resistivity rho, and so the conductors, it has the smallest resistivity, such as silver, but silver is very expensive. So for the electric wire, people tend to use copper. And copper, uh, wait, copper, wait, how to spell it? Oh, copper, silver or copper. But silver is the best conductors. It has the smallest resistivity. And right, and then insulators, it has the largest resistivity, so such as glass. And semiconductors, its resistivity is in the middle, such as silicon. Okay, so by knowing the material, we can look at table to find out its resistivity and the shape of the resistor, and then we can calculate the resistance by using this formula. Okay, and it is, well, this formula is very easy to understand because the larger the area, the larger the cross-section area, and it can let more electrons goes through. Okay, so this area is on the denominator, and so the larger the area, the resistance getting smaller. Okay, which means more electrons can flow through. Okay, and the longer the length, it means more resistance when the electrons traveling through this resistor. So the longer the length, larger the L is on the numerator. So the larger the L, the larger its resistance. So actually, this formula is quite intuitive. Okay. So you can memorize this. It's very intuitive. So there's an example. So you need to compute the resistance. It says water conducts electricity. So okay, so this is okay. So electricity and water can be a fatal combination, as will be detailed in the later chapters. As is also the case with other conductors, water resists the flow of electric current. So pure water, it has a conductivity of this. 182 k ohm meter. However, most water has some addictive minerals or salts and has a resistivity about rho is 175 k ohm meter. Okay, so what's the problem? We're talking about problem. In the water tank of this figure, find the resistance between first points A and B, and second points X and Y. Given rho is 175 k ohm meter, assume that the sides of the tank do not conduct currents. So it's just a simplified problem. So first, it asks you to calculate the resistance. So suppose we connect A and B to some wire. We want to calculate the overall resistance of this water tank. So by using the formula, so we have for the first RAB is the resistivity of water rho times the L is length divided by area. So the conductivity is of water is 175 k ohm meter, and the length between A and B is 2, and the area of the cross section area of this between A and B will be 0.01 square. Okay, so and let's look at the unit. So the unit of 2 is because it is length, so it's m, right? And the unit of this area is m squared. So we calculate, so 175k times 2 divided by 0.01 square, and the unit, we look at k ohm times meter divided by m squared. So we can cross this, and the answer should be 3,500 mega ohm. Mega is 10 to the power of 6. Okay. And same thing for the second problem. So the second problem, it asks you to calculate the conductivity between X and Y. So same thing, Rxy equals, so I just write it directly. The rho is the same, 175 k ohm times meter times, at this moment length is this, length is 0.01, okay, meter, and the cross section area would be 2 times, okay, 2 times this 0.01, and the unit is m squared. Yeah, the unit is m squared. So so we can cross this, So 175k and meter square. So it is 175k divided by 2, which is 87.5 k ohm. Okay, so which we got the solution of our problem number 2. All right, so in this example, we just need to practice the formula to calculate the resistance. Okay, it's quite intuitive. All right, and let's look at the next page. Power and energy. But before we introduce that, I want to introduce the notations for voltage and current. Usually, a capital character such as I, it means DC. Capital I and capital V, it means DC. Okay, which means they are constant. And then, and this, wow, I, V, it means AC. It means AC current and AC voltage. And the subscript, for example, look at this. If you were talking about current, so this is DC current at A, and it means the current at branch A. So we can say is current at branch A. And because current flows through a branch. And for voltage, it means voltage at node A. This is voltage at node A. And they all use capital character. So capital I, capital A, capital V, capital A. So means they are DC components. And for AC components, we use this. We use italic. We use italic character. So we have italic I, italic A, italic B, italic A. It means they are AC. Okay. And oh, by the way, in addition to use italic symbols, we can also use IT, BT to represent their AC values. All right. So, and if it consists of AC and DC component, which is very common, so we use italic I, capital A, italic V, and capital A. It means it has AC plus DC. And if when we're talking about the amplitude of AC, we use a capital character and with italic subscript, and to represent it's the amplitude of an AC current. VA is the amplitude of an AC voltage. But in general, we follow these rules. We use capital character to represent DC, and we use italic to represent AC. So throughout this textbook, they will name their variables following this rule. Okay, and multiplying voltage and current result in the rate of energy transfer, also called power. Therefore, if power is denoted by P, you see it's an italic P. So the assumption is it is an AC power. So they are all AC voltage and AC current. But for this formula, if it's DC, it still works. It also works. Okay. The following equation can be developed. The power of an electric device, and it could be any electric device. If we are talking about a resistor, then P equals IV. You multiply the current flowing through this resistor with the voltage across this resistor will receive the power of this resistor. It means how much energy it is consumed in a unit time. Okay, if we're talking about resistor. So how much power, how much energy it consumes in a unit in a unit time. But we can look at its units. It will become more and more clear. So voltage times current, the unit of voltage is volt, the unit of a current is ampere. And if you remember, volt is actually, it means 1 volt means you are giving 1 joule per coulomb of charge. You are giving 1 joule and 1 joule of energy per coulomb of charge. Okay, right? So it's joule divided by coulomb. And ampere is the rate of charge. So the unit of charge is coulomb, and rate of charge, the unit of rate of charge is coulomb per second. Okay, so you have this, and then you can cross this coulomb, you have joule per second. And joule is the unit of energy. It means if it's a resistor, it means the energy it consumed per second. Okay. And we have a unit to describe joule divided by second, which is watt. Okay. Likewise, if it's a power, if it's a voltage source, for voltage source, we will introduce this later, maybe a voltage source here, and this is a resistor, and same thing for voltage source, it has a voltage, Vs, and it will have, it's having a current, we say it's Is. You see, I'm using the capital here. It means I'm describing I'm describing DC. Okay, so the power given by this voltage source can be calculated as Vs times Is. This is the energy. Sorry. This is the energy that gives by. This is energy. This is the energy. This is the energy given by this voltage source per second. Okay, so it means it could means the power could means uh, giving energy in a unit time or receiving energy in a unit time. And the unit time here we means second. Okay. And so 1 watt equals 1 voltage, 1 volts times 1 ampere. Okay, so you have unit of power called watts, and we use capital W to represent watt. Okay, and let's look at the next page. Okay, that's what I mean. So, sorry, I'm busy. And so, so let's look at this circuit. And so in this circuit, we have a voltage source. Okay, this is a voltage source. It's an active element. And it has, suppose here it doesn't follow what we're talking. So it should be capital I, right? Because right now we are talking about, we are all talking about DC. So let me change it. So it's capital I, the current. So, please wait. 对不起，我在忙. So it's capital I. And then, so this is capital I. So please change it. Minus IV. And please change it. It's IV. Because we're all talking about DC. So, so if this is V, then this is V, right? This is R, because they are in the same loop, and it needs to satisfy KVL. And again, so KVL starting from the bottom left corner, and then so it means so KVL minus V, and then this is plus V is 0. So it satisfies KVL. So if its configuration is like this, then if you are giving V voltage, capital V as the voltage source, then we can guarantee that on this voltage across the resistor is also capital V. All right. So and um, we define in our calculation, we define if it's giving energy, we give it a negative. So so the so the power P1, the power of this is uh, this is the power for the voltage source. So this is voltage source. And this is P2 is the power of resistor. Okay. And so if it's giving energy, so for the voltage source, the current I flows out from the positive terminal. It means it's giving energy. So as long as it is giving energy, we say its power is negative. Okay, so P1 is minus IV. And if you look at the power of the resistor, so this current I flows into the positive terminal of a resistor, and then it is so its power is I times V. Okay, and it's a positive number. So as long as this device consumes energy, then its power is positive. So this is positive, and supply energy is negative power. So we have P1 plus P2 equals 0. It's energy conservation. So within this circuit, the energy provided by the power source, the voltage source, equals the energy consumed by the resistor. So energy, I'm writing down. Energy provided by the voltage source equals the energy consumed by the resistor. Okay, and this is what we do in this class for calculation. But in reality, when you are talking about power, for example, the power of how much power do you need to charge your cell phone? The power here, we always mean a positive. We do not say negative power. We just say power, because if it's a cell phone, that we know it always consumes energy. If it's a power supply, we say power, and then we know that it is giving energy. Only in the calculation we will say negative power. In reality, the we just say power. Okay, it's a positive value. But in the calculation, especially when you are doing homeworks problems, when it is giving energy, please use a negative value. Okay. And total amount of transfer energy between T1 and T2 is you integrate the power from T1 and T2, you can receive the energy that is giving or receiving from T1 to T2. Okay, so we have this formula. And if you want to calculate the power absorbed by the resistor, there are several there are several formula. It can be derived from P equals V times I. And so basically you just combine Ohm's law. So you have this and you have Ohm's law, uh, V equals I times R. So you can replace voltage by I times R, and you have I squared times R, or you can replace the current by V divided by R. So you have P equals V squared divided by R. So these are two other alternatives to calculate the power of a resistor. And if it is not a resistor, if it's a, for example, if it's a voltage source, you need to calculate the voltage across that voltage source times the current flowing out from that voltage source to calculate its power. Okay, so that's the that's the way to calculate. Let's look at the next slides. Okay, we look at this example, voltage direction versus current direction. Assume the direction of current and polarities of voltage shown in this figure refer to the true values. Do the following voltage or current labels conform to how passive elements should be referenced? So we look at this, we look at A, and we keep talking about this again and again. Assume this V and I, they are true positive values. And then so for A, the current flows out from the positive terminal, then it's an active element. It's just like a battery, even though it's a block. We doesn't know what kind of element it is, but we are sure that it is an active element and it provides energy. Okay, for figure B, and the current flows into the positive terminal of this element, so we are sure that this device is a passive element and it always consumes energy. Okay, so this is passive element refers to B. Okay, this is passive element. Okay, we please keep that in mind. Okay, and we look at the next. All right, and for this, we finish the video section right now, and then we will talk about these slides when we come back.